All right, ladies and gentlemen, everyone, welcome back to your EECS 404 course. You might have noticed that I throw 298 up pretty much whenever I have spare time. I was talking with 494 about this. As engineers, you don't really want to think about this very much, but you should. Marketing is an effort thing. It is a time spend, effort, sweat equity thing. What on earth do I mean by that? I used to think marketing was about finding the perfect phrase that would make my tweet go viral, get me adoring fans, sell my product, whatever. In reality, marketing, in my experience, is a lot more of, did you put in the 2 or 3 extra hours to make your portfolio site look good? Did you put in the 2 or 3 hours to post some flyers, to message some people on Discord, to send emails to the right people, to, pester and poke the Discord server admins for an announcement? Did you remember to do these things? Did you remember all the places you're supposed to do this? Have you shilled your stuff enough? Not to the point of being spammy, but to the point of forcing people to actually notice it. And if you do these things, you get better numbers. And if you don't do these things, then you get worse numbers. And that's what marketing tends to be. This is all to say that, as a reminder, you can't just make great things like the game engine you're making. It's awesome. It's ridiculously cool that you've done this. Students never do this. MSU has the world's best public game dev program. They don't have this. Their students don't make their own game engines. They can't. You can. But that doesn't matter if you cannot get people to know that you have your own game engine. If you can't find a way to put this in front of a recruiter, if you can't find a way to bring this up during interviews, then it doesn't matter, okay? So I really want it to matter for you. I'll tell you, many of the most successful people I've ever met, they aren't the best academically. They aren't the best programmers. They don't have the coolest projects. What they do have is absolutely zero fear. Okay? They have no fear. The people who are super successful are the kind of people who today would cold call Sid Meier himself. Hit him up. Yo, what up, Sid? I'm a student at U of M. Do you have any jobs for me? Like, dude, you can't just do that. And then they go do it. And usually it doesn't work, but sometimes it does. Okay? And that is all they need. It's absolutely incredible. Okay? I'm way too much of a chicken to cold call Sid Meier. And I've already met the guy. So just keep that in mind. Anyway, the reason I bring this up is, Austin, why are you putting 298 up here all the time? It's because I'm trying to get people to notice it when they walk through the room. That's it. What is that? Oh, big logo. And then once they see one course of mine, they tend to filter and flow to my other courses. This is just a big marketing strategy that I have, okay? So thank you for enduring my shilling. But if you're curious why I do that kind of thing, it really matters, okay? The bigger your course is, the more power you have. The less at risk of getting laid off you are. This stuff really matters. It really does. So, anyway, everyone, welcome to this week of EECS 404. We are really not far away now. We are right in the middle of your homework 9. Student has already finished homework 9. You know who you are. They gave some really great feedback. They said the performance requirements for homework 9 still were not as stiff as they could be. One really powerful thing about data-oriented programming that we don't really require in homework 9, but I think I will next semester, when you get your code into a kind of a data-oriented setup, where you have these simple systems, these simple bits of logic that are just iterating through a bunch of actors and processing different components, different bits of data that you care about, very often this lends itself to multi-processing, parallelism. Why? Well, I'm going to show you in a sec why. But someone on the Discord server was asking, why does the new game development track require EECS 482? EECS 482 is one of the game dev courses, right? The courses we want you to take if you want to complete the game dev track. And I chose EECS 482 because I thought multi-threading was a very important concept to have some experience with, okay? This class doesn't really require it. For auto-grading purposes, we don't do a whole lot of multi-threading, but I think I can find a way to put it into homework 9. And the reason is because when you can get a data-oriented approach to the way your components and logic and systems work, usually that problem becomes embarrassingly parallel. And if you have 1,000 particles and none of the particles depend on each other, and you don't have a whole lot of branching, you don't have a whole lot of shared data, you can easily just ask a few of your processors or threads, your processing units, to just, hey, you take the first fifth of this for loop, you take the second fifth, third fifth, fourth fifth, final fifth. That's it. That's it. All you have to do. And now it's using your processor to its full extent. So I'm going to show you a little bit of that today. I'm going to point it out at least. It's not a huge topic for this course, but I think I'm going to beef up homework 9 next semester to actually require this. I have to find a way to do it in a way that is going to introduce multi-threading briefly in a way that won't confuse people who've never seen it before. And then in class, we can talk a little bit about multi-threading, not all of 482, but just a tiny bit, because I really think it is fairly important, okay? Okay, anyway. All right, so that is the end of my tangent to start the lecture here. Did you know, oh yes, question.
Yeah, the game dev track, if we hit all of the class requirements, do you get anything for it, or is there just like a recommendation?
So that's a really, really great question. So I think hopefully I can Google it by now. UMich CSE tracks. Uh-oh, I don't see it anywhere. Is it in here? Do you know if it's in here? Is it in here? Tracks? Tracks of study in CS. Here we go. So if you don't know what a track is, a track used to be a thing. It was gone for about the last 5 or 6 years. But it used to be a thing, and it was in the course guide. It was buried in the course guide. So you say to yourself, well, wait a second, is that like a minor? That's kind of what it sounds like, right? You're getting a computer science degree, but you're kind of specializing. So you've got the AI track, very popular these days, I imagine. And the AI track has a certain number of courses they want you to take. There is the data and information track. There's the game dev track, which is really, really cool. And so if you complete a track and take all the courses we'd like you to take, what do you get? A big old pat on the back. If you can list that you did the game dev specialization on your resume or track, and that can be useful for your resume. If the employer calls us, we can verify that you did the track and completed it. But other than that, it unfortunately won't show up on your diploma. I think we might be working on how to get it onto your diploma, but really, it's more like just a guide. If you're into game dev, here's some courses you should take. Where is EECS 298? Where's EECS 494? Where's EECS 440? Okay, only upper level CS courses are allowed in the track, okay? So I tried to get them in, and they told me, no, it can't do that. So 404, 471, 482, and another one of your choice. Probably going to be MMO architecture up there soon when I get that one done. But they won't let me put a 498 in there either, so we have to wait until it's a permanent course before I can put it in. Man! Crazy. Okay.
I might be wrong on this, but I believe you can get a letter from the college.
That's cool.
That is pretty much like a certificate, but you have to specifically ask for it.
I'll write you a letter if you want. Keaton was awesome. He took a bunch of my courses. I can even make it, I can print it in a really good printer, and we'll put a custom logo on it and everything. I'll even sign it. All right, anyway. Okay, so it's not that important. It's mainly a guide to help people who don't know what courses they should take. This is something you might consider, okay? It's a really shame that we can't put the other courses on there, though. So anyway, all right, so Blender Game Engine is our game engine of the day. Blender used to have a built-in game engine, which is really, really quite a cool thing. All the 298 students and future 298 students like, oh, that's awesome. When I was in middle school, I remember using it. I think it used Python, yep. And unfortunately, it didn't really work out. Not a lot of people used it. It was discontinued and removed from Blender in 2019. But fortunately, it had enough fans that a group of fans of the Blender game engine, they forked Blender. They forked Blender and they created the UPBGE. What a name. This is not the Upper Peninsula game engine. This is, I don't even actually know what this means. This is an awful name. I think sometimes our open source leaders are not they're not really thinking about marketing and how important that is to actually getting usage and how important usage is to the evolution of an engine. Because I would never choose this particular name. But in Blender, you of course can make models, you can animate them, you can create beautiful particle effects, there's a built-in physics system. Blender is mainly meant for authoring of 3D content, but this engine allows you to stay within Blender and program logic and spawn things in. It allows you to go ham on animation and integrate the animation with your logic really effectively. So when you look at this character just animating beautifully as they run around in kind of an action game kind of game, this is something you can do. It introduces prefab system like you'd expect. It introduces a bunch of UI that makes it a bit easier to populate game worlds. If you look down here, maybe I can copy video link and make it a bit bigger. So this still doesn't look that good. But what you can see here is that you have kind of an Unreal Engine style blueprint visual logic system. Okay, so it is programming. It's visual programming. And so people who are not really into textual programming, who don't want to write a bunch of Python, can write logic this way if they want to, which a lot of people really, really appreciate. So I've never heard of an industrial commercial game that shipped with this engine, and I don't think it's easy to find any out there, but it is there. It's distributed as a modern version of Blender. Typically what happens is that the team behind this project, they will grab the latest Blender 5 that comes out. And they will then kind of bolt their stuff onto the new version of Blender. So you get the new features of the latest Blender release, and then you get the game engine specific stuff that they want to add in. It uses the open source Bullet 3D physics system. We, in this course, use Box 2D. That is the Angry Birds two-dimensional physics system. But if you want to have a 3D system, which you probably will want if you introduce 3D rendering, then you might go for Bullet. You might go for Bullet. You might go for NVIDIA's PhysX, which I think is a little bit chunkier, a little bit harder to integrate. But this would be a really good exercise in getting 3D physics into your engine once you've got some basic OpenGL figured out. Okay? Anyone have any questions or comments on the engine? Yeah.
I saw that this engine, I looked it up, it's also GPL, so you can't really, it's going to be hard to make a commercial game out of that.
You know, I think, is Godot MIT licensed?
Yeah, I think so.
So the thing with GPL stuff is that you can use it as like a separate tool. You can't usually integrate it into your final software build. So, I guess that's not going to work, is it?
Yeah,
man.
Because I think if you use the engine itself, if the engine code is written in GPL, then you got to make your game GPL.
Yeah.
And if you make assets in Blender, it then produces something else. That's
fine.
That's fine.
Yeah, that stinks. You wonder if maybe they would say, well, the tooling is GPL, but the final binary produced from the Blender game engine is MIT, or it's not MIT, it's whatever you want it to be. Like that would make it an actual feasible engine, but if they actually are GPL and the binaries, the output binaries are GPL, complete non-starter, okay? Almost no one makes open source games. They want to make a game, they want to sell a game, right? That makes it really hard to do, especially for indies who are going to be using this. Okay, anyway, we have some extra credit for you. I think you get extra credit in this course by going to IGDAs. You don't get a ton of it, but you get a little bit. So Jerry Cortez, who is an associate producer at Stardock, is going to be walking us through the history of the hero shooter genre, in particular the last decade, which has seen the rise of hero shooters. Do anyone play Overwatch? Anyone play Apex, Overwatch? Anyone play any other hero shooters? Highguard? Concord? Okay, so there's going to be some morbidly funny stuff at tomorrow's presentation, and also probably some pretty sad stuff. In any case, I'm sure it's going to be a great lecture. I'm sure you'll enjoy it. And you come, you enjoy some free pizza, and you can show off your game, show off your engine if you want to during the dev lounge from 6 to 7, or you can just show up at 8:30, enjoy the talk from Jerry, and then peace out and get some extra points, okay? Anyway, if you have any questions about that, let me know. The next quiz is happening Monday. You can see that right here on the schedule. And it's not going to be too bad. The topic is going to be box 2D stuff. So, what is a B2 body? What is the hierarchy that we've seen in the lectures, right? So you've got this B2 world, and then within that world you have B2 bodies, but a body might have B2 fixtures, and those fixtures might have B2 shapes, right? So that kind of stuff, understanding how you do things in Box 2D is going to be valuable to you. There will be some simple questions on the topic of data-oriented programming. So that really shouldn't be too bad, all right? We have last year, Nick Cerrone, awesome. Thank you. Awesome game engine architecture student of mine last year. He decided to bite the bullet for all of us. I am too lazy even to create engine API documentation for the A2 engine. But if you find yourself making games with your engine, then you might enjoy using his reference, which I don't think has changed at all since last year and doesn't need to. But you have here a nice little reference of what the different classes can do, the Vector2 class, tables, the application API, what the functions do, how to use them, what the parameters are. I find myself forgetting what the order of the parameters is for my functions, and so I always have to go back to the homework 7 document to actually see what the calls need to be and what the parameters are. In any case, if you want to use it, then go for it. I think I've told this to a few of you. I really wish I had a class. I wish we had a program here in which we could take EECS 281, an early required course, and that is game engine architecture. Every student builds their own game engine, at which point every elective course that follows that can assume we have our own game engine and that game engine conforms to a certain API. And then we could do EECS 494, but instead of Unity, we're using our own engine. That'd be crazy, right? And then, of course, we would have separate courses for learning Unity and for learning Unreal because, studios want that kind of thing. Anyway, just kind of me being wistful about what we could one day have, maybe. I don't know. Maybe I have to move to MSU to get that kind of thing. All right. So we didn't have much to finish with our previous lecture because we're not going super deep into ECS. This is going to be a very short lecture in general. We are going to talk about coroutines, and if we end early, we'll have some extra office hours. Let's go ahead and just finish this up, do a quick recap as well. The main idea for data-oriented programming is that we really want to be thinking about our cache. All right, we want to be thinking about our cache to utilize our hardware as effectively as we can. We don't want to be loading unnecessary data into our cache, as that will slow us down. It will cause cache misses, and that will cause a lot of problems. You can see the main difference between object-oriented programming on the right and data-oriented approaches on the left here in the ideal situation. And it should be pretty obvious why one of these is faster than the other. So the typical approach to getting kind of a data-oriented setup is to try and break your objects out into arrays. So object-oriented programming is arrays of objects, which you're used to, and data-oriented programming is said to be objects of arrays. But really, you can just say arrays, okay, or array properties, or properties represented by arrays. And so you will often do something like this. You will break out the properties of your objects into these arrays, and then you only access the arrays that you need to in order to complete some sort of computation. That means you get to ignore and not load in all of the other values that you don't really care about as much. And that can help you out. One really cool thing here is that if you look at this, there's not much branching at all. And if you look at this, this is an extremely easy computation to parallelize. If you have one thread, then you can simply have that one thread run through all 1 million actors or particles that you might have. Just process them one after the next. But the really cool thing here is that particle 2 doesn't have any sort of dependency on particle 1. Okay? And so you can actually, if you say we have 5 or maybe 6 or 8 threads, maybe we have 4 processors and each processor has 2 kind of physical threads that can run independently. You could say, well, you know, we have 8 threads, and so let's take 1 million actors divided by 8, and we can figure out what range in this for loop we can assign each thread to. And there's going to be some startup costs because, you know, launching a bunch of threads is not a speedy thing. Often you will have a problem like this where you say our number of actors is not high enough for us to even bother launching additional threads. You might say, until we have 1 million actors, we're just going to stay at one thread. Keep it single-threaded. But as soon as we have more than 1 million actors, maybe then we try and split it up and then launch a bunch of threads to knock down the problem. But the main thing here is that if you can get your data-oriented programming going and get into this kind of approach for solving your problems, you can usually parallelize this kind of thing, and it's not very crazy. It's not that hard. And also, you don't really need mutaces. Often you don't need as many synchronization constructs, which is really nice. If you recall from our data-oriented, so let me see here, our latencies. I think it's up here, our latencies, yes. Okay, if you recall from our little latencies thing here, by the way, you might want to study or at least remember where this slide is, okay, for the quiz, just saying. If you look at this, right, a cache miss is a really bad deal, 100 nanoseconds, right, 100x time. But having to use a mutex and like lock and unlock it is also a slow operation, typically. And so if you can avoid having to use a bunch of synchronized data structures and constructs like mutaces or a semaphore, have you ever heard of like lock-free programming? Have you ever heard of that? It's this idea that we can create data structures and algorithms that don't need locks. They don't need mutaces, and yet they still work on shared data. I'm not exactly sure how these work, but it's really interesting. And for high-performance, multi-parallel stuff, it's something that you would probably want to learn someday. Okay? All right. So that's the basic idea here, and you really are getting to what feels like kind of a relational database kind of situation. Let me see here. Okay. Now, this is not all just an easy win, okay? In this course, we won't really go deep into it, into ECS, but you start running into some problems, okay? When you start going, ECS, you start going data-driven, you really start to want to gain the ability to add components onto actors. You want to do all the dynamic adding of components, removing of components, manipulation of actors and objects and their data that we do with object-oriented programming. But unfortunately, data-oriented programming can make this a bit harder to do. So data-oriented programming and ECS systems are extremely popular on consoles, especially, where resources are very, very thin and you need to make that hardware sing. A cache miss could be devastating on consoles, whereas on the autograder and on your computers, maybe it's not that big a deal, okay? Maybe you don't really notice. Something to think about, let's talk about what ECS means, okay? ECS doesn't mean what you think it means. It stands for Entity Component System, and these are all familiar terms. Why? You have made games before, chances are, which means you've used components, something called components. You have created things that sound similar to entities. An actor sounds similar to entities. It's a synonym, right? A game object from Unity is an entity, right? It's not. And you've created things that you've probably called systems. Like in 494, we create a toast system. We create a player management system, a particle burst manager system. But these are not systems, okay? In the context of an ECS, component, system, and entity mean very specific things, and they often are kind of different than what you're used to. And that's why I really don't like the name of this, ECS. Okay, components in the context of an ECS have no logic at all, which means that the components, the Lua components that you have, yeah, those aren't considered components in an ECS data-oriented context. What is a component? Well, in an ECS, a component is basically something like this. It's a little package of data associated with an actor that is usually kind of grouped together, okay? So chances are, if you are doing calculations related to position data, you don't just want the X, you also want the Y, you also want the Z. Chances are, okay? A physics component might have velocity on the X and Y axis in it. A living component might have HP, hunger, health. Some of your actors are going to have some of these components, and other actors won't have these components. This is just something to keep in mind. In an ECS, a component is just a container for data. It usually doesn't really have functions inside of it, okay? The logic that acts upon this data is elsewhere, okay? It is small, which is kind of nice. It's easy to reason about. Components will typically sit in some sort of typed contiguous container, which gives you the performance improvement that you are looking for. It's probably the reason that you are using data-oriented ECS in the first place. You know what's really interesting? A quick tangent story. Unity was kind of introducing their high-performance ECS DOTS framework. You know what DOTS stands for? Data-oriented tech stack, I think. Oh, what's going on? Hold up. Unity DOTS ECS. So Unity has what's called a data-oriented technology stack, and it's this big feature. It's supposed to speed Unity up a great deal. I remember in, I think, 2016 or so, maybe, they were really rolling this out. I was on the plane to San Francisco, and I was sitting next to like Unity's, I don't know if it's their CTO, but it was like someone who was very high up in the technology side of Unity. And he was showing me how they were using AI to basically guess where shadows were going to appear. And I look at the demo, he's like, man, this is really cool, right? And I'm like, yeah, this is cool. And it was really unusable. Like it's flickering and really kind of nasty, but it's kind of a neat idea. And we were talking about DOTS. He was asking me, how DOTS was going, because I taught a Unity course at University of Michigan. And I told him, yeah, we don't use DOTS at all. And he was kind of confused about this. Like, why don't you use dots? I don't need the performance. And it's new, and the documentation stinks, and it kind of doesn't work yet, right? And it struck me that I don't think anyone chooses Unity for performance reasons. Why does someone choose to use Unity?
It's industry standard and it's free.
It's free, it's industry standard, but so is Unreal Engine. Why does someone choose Unity in particular? Yes?
Because there's a plethora of just resources out there for it.
Yep, same thing with Unreal. Unreal's not quite as good. Unity is the engine you choose for accessibility, and because it is a nice beginner grade integrated engine. It's not quite as hairy as Unreal Engine. It doesn't have as many features. It's not bleeding edge. But people teach Unity at universities for a reason. It is a strong engine that is geared toward teaching new people. And so this is to say that, just a reminder, performance is really awesome. Get it if you can, but don't sacrifice your engine's soul for it. Because years later, almost no one cares about dots and ECS in Unity. As far as I know, very few games use it. And the ones that have kind of regretted it. City Skylines 2, big epic disaster, in part because they chose to go for the ECS approach within Unity. Yes?
I think they're, just recently they added ECS as a default package in Unity 6.4.
Okay, cool. Took them a while, didn't it? Yeah, so we'll see if people end up using it, because it turns out you have to kind of change the way you program a little bit away from the component-based approach that everyone's used to if you want to use ECS. Anyway, let's keep going. This is not a big lecture, so I'm allowing myself to get more distracted than normal. Hopefully it's interesting to you. So all components are going to be small. They're going to sit in these typed contiguous containers. This is exactly what you want. And it might look like this. You might have a bunch of arrays like this. So entities are not really actors or game objects anymore. They are just an index, okay? They are a number. And that entity is going to be kind of how you index into these arrays to grab the thing that you want. Now, it's a little bit more complicated than that, because a high-quality ECS is going to solve some pretty gnarly problems for you. Here, you have an example of, hey, we're going to update a particular actor's position. So we're going to go grab actor 0's position component, and we need their physics component because that's where the velocity is stored. And then we're going to use just these two things. Actor 0 might have a living component, but we're not going to grab that component because we don't need to load that data into memory. In an object-oriented approach, we would have to load all that data in, and that would start causing some problems, okay? So here's something that's fairly different with data-oriented programming. Logic isn't inside the components, so where is it? Well, in an ECS, you often get a bit back. You get back to the more imperative programming style that you might be used to in EECS 280 or EECS 183, where you kind of have centralized code and you're not breaking it out into a bunch of decentralized components. A system is a chunk of logic that is going to process a bunch of actors, okay? Often, a system will also be annotated somehow to say that this system only wants to process actors that have certain combination of components. So we don't want to be iterating through actors that don't matter to us. An actor that doesn't have a position component and a velocity component can't be moved. So a physics system in this situation would basically basically iterate through the actors that are confirmed to have both of those two required component types, and it would only load those components for those actors, okay? Thus saving us a lot of performance in both of those ways. Now, how it accomplishes this is a little bit more of a funky situation, but it might look something like this. It might literally be a function This is your system. It doesn't have to be a class or anything. It is just going to iterate through the actors that it cares about, and it is going to grab the components it needs and then do its processing. Now, in a more mature, awesome ECS, what you'll see here is not just like num actors. It might look like a for each loop, and it's going to make a function call, get actors that only have these two types of components. I think there's some like static polymorphism that happens in which it's able to basically figure out that this system only wants these actors that have these components, and it's able to kind of make that work in a very fast fashion at compile time. I'm not entirely sure how it does this because I've never made my own big ECS. I've never had a reason to. But part of the difficulty in making a mature ECS is making all of this very fast so that you have those performance benefits. Because if you try and make an ECS and you mess it up, you don't really get any advantages. It's not much faster than the normal approach, but you've made things a lot more awkward. Okay, so we are iterating here through a bunch of small objects that are stored contiguously. We have standardized logic for every actor that we process, which can be nice. Sometimes it's considered easier to read. If we have access to multiple hardware threads, then this becomes extremely easy to parallelize because each particular actor doesn't depend on any other actor. If you do have logic that causes actors to kind of depend on each other, sometimes you need to have multiple steps where you run through all of your actors once to basically kind of cache which actors need to mess with each other, and then you run through that again and actually process that stuff. And that's how you can kind of sort of parallelize that. And some people find this to be much easier to read than your typical component full of C# and dependencies and stuff. So, maybe you choose to go this route for clarity reasons and not just for performance gains. My recommendation, if you want to start messing with an ECS, is to go grab some online. There are C++ ECS frameworks that have been developed. I think they do a bunch of interesting compiler and templating tricks to get good performance. Let me see here. CPP ECS. No, that's not what we want. Entel, or Ent. Let's check it out. So we've got Ent. Let me see here. Gaming meets modern C++. Blah, blah, blah. It's a header only, which is, convenient for us to integrate. Tiny and easy to use library for game programming. Written in modern C++. It's used in Minecraft, apparently. That's a pretty amazing, bullet point for the resume, isn't it? Blah, 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 blah. Okay, where is the ECS stuff? Code example, huh? Okay. So, let's see here. The entity component system, also known as ECS, is an architectural pattern used mostly in game dev. And you can read more about it here. It started off as a pure entity component system. Over time, the code base grew, and it added a bunch of other stuff. Okay, so what do we have here? We have position, velocity, structs, update. It has a registry system. Okay, it looks like it might be registering that we care in the system about position and velocity. So actors that have these things will be included here. View.each. This looks like a for each loop, possibly. We are iterating through view each. We only get the entity and its position and velocity. And we use this kind of templated function to get those things. Okay, yeah. So this kind of looks like an ECS. Benchmarking. You can read about this kind of stuff if you want to. One problem that these are meant to solve is a problem we mentioned the last time, okay? If you have a bunch of your components in these arrays, and each actor is just an index into these arrays, how do you add a new actor? Well, you have to add one more column to each of these arrays. And you need to add a column to all the arrays in the easiest implementation. But that stinks. What happens if you want to create an actor that has a position, but it never moves. So you don't want to give it any physics, and you don't want to give it any living stuff because it's just kind of maybe a static platform. Okay, it's a tile. Well, what do? We have to add another entry to each of these unrelated component arrays, and it's just going to be wasted space. And this waste gets worse for every new component type and every new array that we add. So we end up with a very sparse matrix of data. Okay? Not good. We're burning a ton of memory. And especially on consoles and mobile devices where memory is a little bit premium, that's a big problem. So how do you add a new actor? How do you delete an actor? If there's an actor that we want to delete and it happens to be, 3, or it happens to be actor ID 500, but we have 1,000 actors we've created, then do we just zero them out? That's wasting memory. It will work. It'll be correct, but we're wasting memory. Can we shift everything around so that things still work? Maybe. What if the actor has a middle ID? What if some actors don't have some components? How can we save space? How do we make sure we only process actors that have the exact combination of components our system needs? Otherwise, we can't really do anything with them, okay? So solving these problems is something that an ECS does. And I think there are some unique data structures that can be used to kind of keep things mostly contiguous and cache-friendly, but allow you to still kind of move things around the heap and to resize things without causing things to move. I think those tend to get used quite a lot in an ECS implementation. But that is a topic, I think, for another time. So I want to talk to you about the topic of coroutines. Coroutines are an extremely important kind of game designer-friendly technology that have started to show up basically everywhere, including in C++. C++ 20, right, so reasonably recent, added support for coroutines. I'm going to show you what they look like in a bit. Scripting languages often have coroutines, and how many of you have taken EECS 494? If you've taken 494, then you know just how valuable coroutines are to game designers and gameplay programmers trying to write features that take place over time. So I want to show you a small little lecture. For the 494 students, you may find this to be familiar. I want to show you some game mechanics that are extremely difficult to script, okay? The normal way. These are things that the 494 students need to program, and so they have to figure out a good way to do so. Check these out. These are room transitions in The Legend of Zelda and Metroid. Let's take a look. First, an ad. Okay. What is this? Electrical services? Does anyone need that? Electrical services. There you go. Won't burn your house down. Free estimate today. Sweet. Okay. Why can't I hear anything? Oh, here we go. That's why.
I'm telling everyone. Barber, dentist, I got a hardware guy. We're going to add him.
Get the Samsung Galaxy S56 Ultra on the trade in any condition. Most expensive plan not required.
Okay, so that was actually a transition. But watch this, okay? When Link walks into this doorway, we're going to do a few things. We're going to turn the controls off. We're then going to wait for a couple seconds. We're going to move the camera. Then we will spawn Link in at the other side and turn his controls back on. Watch this. Ready? There you go. That was it. That room transition. It is simple in its idea, right? It's very easy to explain. But this is actually extremely difficult to program unless you use coroutines, okay? What about this? Many games have mechanics that play out over a certain amount of time. Samus is going to unlock the door here. Then she's going to walk into an invisible trigger. The game's going to disable her controls so she can't move or shoot. The camera is going to move over a course of like a second or two, and then we re-enable Samus's controls, and I think we even close the door a few moments later. Watch this. There we go. And cool. So what's so hard about this? Well, the thing is, you are used to writing code that all executes as fast as it can, okay? In EECS 280, when you write a piece of code, your code goes flying down the page as fast as it can. If you want to stop your code and let it breathe, let it chill out, do you know of any functions that can let you do this? There's a famous function. In fact, you implemented it, I think, in application table in homework 7. What is it?
Sleep.
Yes, sleep. Sleep is a very famous function that will basically take the current thread and it will tell it to chill, relax, okay? Don't do anything. Unfortunately, that's not going to work for mechanics like this because we don't want to completely stop the current thread. We want to do other things and then come back to our current stack later, okay? And that's just something that you don't usually do. So in this door transition, the player hits the door, that's a trigger. We disable the player's controls. This is probably just a global Boolean value, like controls enabled. You flip it to false, you turn off movement. You flip it to true, now all those if statements relating to movement will succeed. We move the camera over 2.5 seconds from one location to the next, and then once that camera movement is finished, and not a moment later and not a moment before, we will turn that Boolean back to true. We will re-enable the controls, okay? So what's the problem with this? Well, you already kind of know how to do this. Now, this is C# code, but it's very similar in Lua, okay? In homework 8, you implemented on trigger enter, on collision enter. Disabling and enabling player controls is just flipping some sort of global Boolean that you've created in Lua. It's too easy to create global variables, okay? In C#, this would be a public static variable on a class called player. Here is the major problem, okay? In one frame, we can't do all of this, and yet most of our code executes in one frame, okay? Temporal mechanics that span multiple updates of our game, multiple frames, are actually really tricky to implement. Okay, they're very messy. Often you have to introduce a lot of state. You have to have a bunch of Booleans keeping track of where you are. You need a bunch of floats to make timers work. You could try multi-threading. Okay, why not? But actually, Unity, the scripting layer of Unity, where you write your C# code, is single-threaded. So this ain't gonna work, okay? Lua is single-threaded, which means you can't try this approach either. You could try the famous sleep function, but if you try this in Unity, it's gonna freeze your entire game. It's just gonna freeze, it's gonna lock until it stops sleeping. That's awful, a terrible solution, okay? And it's a bad solution to Lua as well, it won't work. You might try asynchronous programming. Some languages like C# provide something like await, and this allows you to basically tell a current, basically stack, a current context, to just chill and let something else run for a while. It's like asynchronous programming. You see this in JavaScript quite often because JavaScript is constantly downloading things and waiting for downloads and running some code when the download finishes. But await isn't available because Unity doesn't use a modern enough version of C#. And this might be one of the reasons why they refuse to upgrade or why they're slow to. You had your hand up?
Yeah, I was just going to say, Godot has to wait.
Yeah, it does. Yeah, which is kind of funny, isn't it? However, it does not work in web builds. So that's a big pain in the butt. Yeah. What does work in web builds are coroutines. And what's interesting, so all the Unity devs out there, coroutines are not a Unity-specific technology. It is specific to C#. So one of my first things I did when I switched some of my projects to Godot was I brought over my coroutine technology from Unity and I had to like create my own coroutine manager, but it was able to work. And now I have full coroutine support, just like as if I were in Unity. It's not a Unity thing. It is it's not mostly a Unity thing. It's mostly a C# thing, okay? All right, so here's the kind of code we would really like to be able to write. And even if you haven't seen much C# before, hopefully it still makes sense. We have onTriggerEnter, a function that fires. The engine calls it for us. We detect, what have we touched? Well, we've touched an invisible trigger that has a tag on it or a name called door west. So we want to perform a room transition to the west. That means turn off the player controls. That means move the camera and then turn them back on. We would really like to be able to write a beautiful, crystal clear, no extra state function like this. This function, perform transition west. It turns off the player controls, and then we move a game object, an actor, over a certain amount of time. The actor we want to move is the main camera game object, and we want to take 2.5 seconds to do so. And then once this function is done processing, we just turn the controls back on. This is beautiful code. It's easy to read, and it reads just like a to-do list. You could give this to a human, except it would say like, go to Myers, buy milk, go home, right? Purchase the stuff and then go home. Otherwise, you get arrested, okay? This is going to fail because we don't have the ability to write this function without using coroutines, okay? The big problem here is that we cannot write the move game object over time function. Why can't we write it? Well, by default, a function is going to run as fast as it can. And it's going to do everything it can on the current frame. In fact, the current frame will not end until that function is done with its business. And yet, the function, in its definition, it is supposed to do stuff over the course of multiple frames, over time. It is not supposed to just rush to the end of its job. And so we have a contradiction here, okay? And we need a way to tell a function to chill. We need it to yield into the future. We need it to just relax, okay? And if you're confused about what coroutines are, you can think of them in that way. It allows a function to relax and chill and just relax for a bit and let everything else run instead, and then come back and finish up later. This line right here needs to be able to pause its own execution for the 2.5 seconds that it needs to do its business and move that object over from one place to the next. And so normally we just can't actually do that. If we use thread.sleep or a sleep function, it will just pause everything and it will just totally fail, okay? We can't halt the thread. We have to keep the thread going. The thread is still running. We just want the thread to run some other stuff and then come back later to this point in the call stack. Unity single-threaded, Lua single-threaded, so we can't create new threads and we can't block on them. That's not going to work, okay? We could introduce a ton of state to create a state machine class, for instance, and a bunch of different child classes derived from that parent class, and oh my goodness, what a mess, all right? We could do what I've seen a bunch of students do, which is they keep like a Boolean, which is like, has the camera reached the destination yet? Equals false. And then every frame we check how close it is, and then we eventually set it to true, and that triggers a bunch of other logic, and it's a mess. It's a horrible mess. It's hard to follow. It's super buggy. We want to just be able to write this beautiful code, like a to-do list to the grocery store, okay? No extra state, no nasty logic that makes no sense, okay? The solution that Unity introduced for us, they didn't introduce it, but they kind of made it prominent and they advertised it, they created a good API for it, was to use coroutines. Coroutines, a feature of C# and a feature of Lua, it turns out, and now a feature of C++. Coroutines allow you to write exactly the code that you want, okay? And so, here is our first ever coroutine. You may not have seen a coroutine before in your life, but I want you to read this code and think about what it might do. when the game starts, we are going to start coroutine, and this is the coroutine we want. What is that? Well, it's just a function. It's a function with a very particular return type, and it has that keyword that we were talking about earlier, a yield keyword. In fact, the actual keyword is yield return. I know it looks like two words, but it's really a package deal. You can think of it as one keyword, yield return. So I want one of you to perform this coroutine for me. Be brave. Any theater kids in here? I'm so jealous of theater kids because they have no fear. And that is so very powerful. And it annoys some people actually. But actually, I think it's envy. Okay? Any theater? All right. Are you a theater kid?
No.
All right. Well, good enough. Okay? Go for it. 3, 2, 1, action.
Hello. There.
A little bit fast, but very good. Okay? So, hello. There. Okay? It's very awkward hello. It's like delayed. In fact, someone will probably start talking to you, and then in the middle of their sentence, you're going to say there, and then your social score just went down like 100 points when you do that. Okay? So, what's happening here is that we have our life cycle function. This start function will be called when the game begins or when this component is created. And we will call into and execute this delayed hello function. Now, we have to be careful to launch this function with the start coroutine function. Otherwise, it's not going to work the way we expect. Unity provides this start coroutine function to us, and Lua does something very similar. So this is a coroutine. It's a very special function. And you know it's a coroutine because it returns the very special data type I enumerator. Now, this probably makes no sense to you, I enumerator. But what this data type, what this return type will do is it will tell the compiler to take this function and chop it up. Okay? Basically, it's kind of creating a state machine for each line that is possible of iterating through each line of this function without kind of losing where it is if it yields. So we launch into this delayed hello and we immediately print to console hello. Okay? Then we get to this line, yield return. And this is a key word. Whenever you see this, it means the current function is going to peace out. It's going to relax. It's going to chill. It is suspending. It is yielding itself so that other things can run. We can jump around the code base. This call stack will be saved, and we'll return to it later. When will we return to it? You don't need to know what this object is, but we're creating a new one. It's called wait for seconds, and we have a 3. So this is a special kind of yielding object, which you can yield on, and it will end. It will stop yielding in 3 seconds from now. Okay? And then we wait, we wait, we wait. Everything else in our game is running. The rest of our code base is running. Okay? And then boom, after 3 seconds, the coroutine knows to return execution right here, and then we print there. Okay? So what we have here is a function that can let other things run. It can yield on a single thread. Amazing. You probably didn't know single threads could do this. A single thread can jump around a code base, and it can suspend execution of certain functions so that it can run other functions, and then come back to the previous suspended function and continue from there. Normally, that's not something that a single thread really can do. But because of coroutines, we can now do that. Okay? These are the things in Unity that you have to have for that to be a coroutine and for it to be successful. I'll show you what a coroutine and a coroutine manager looks like in Lua. We'll run the code together and then look through it in just a moment. But this is a lecture borrowed from 494. So that's why it is the way it is. Okay, so I have another more complicated coroutine situation for you. It turns out coroutines can call other coroutines. And these coroutines can run in parallel or they can block. And one coroutine can wait for another coroutine to finish. Very useful. So I want you to look at this. Hopefully you don't have to squint too much. You can always go and look at the stream if you want to see this up close. But I want you to study this more difficult program, and I want you to then act it out for us, okay? Okay, who's feeling it? Go for it, Keaton. You got to stand up, though. Be loud.
Hello. There.
Good job. Almost perfect, okay? But there was a delay between your hello and your first hello and your first So it's like the game starts, it's hello, there. Okay, if someone walks up to you and does this, it's like, watch out. Okay, so, there was a time in my life when I was about that awkward in like elementary school and middle school. I think I was just a late bloomer or something. So here's what's happening. Okay, the game starts. We launch into this coroutine. Remember, you need that start coroutine function or the coroutine won't continue successfully. Coroutines usually need to be registered by some object that will re-enable them and get them to keep going. Something has to reactivate the coroutine once you suspend it. In Unity, when you call start coroutine, you are registering this function as a coroutine, and the component itself will be responsible for enabling it and checking it when the time is right. So we go into delayed hello, and we do our hello function right here. We print hello, but then we immediately yield return, not to an object, but to another coroutine. We start that coroutine, we are blocking on it, so we're going to wait for this coroutine to finish. This coroutine has a 3 that we're sending in as a parameter. It is just a special kind of function, after all. We go in to do some humming, and our int number of notes value is 3. While 3 is larger than 0, we hum, and that's why we immediately hum, because we haven't actually waited yet. Okay, we haven't actually waited for any time yet to do the hum. So we go hello and then immediately do hum on the same frame. We then decrease our number of notes variable, which was 3, down to 2, and then we do yield return new wait for seconds. You've already seen what this object does. It waits for 1 second, so 1 Mississippi. We go around, 2 is larger than 0. We hum again. Now 2 becomes 1. We wait 1 Mississippi. We wait, and then we go around one final time. We go 1 is larger than 0. We hum a third time. Our 1 variable becomes 0, and now we wait. Now we go around the while loop. 0 is not larger than 0, so we break out. We finish this coroutine. It's done, and that means we return to the previous coroutine, and we print there. Okay? There you go. And every time we hit this new wait for seconds line, we are going to wait for 1 second. And everything else in our entire program can run. Other components are running. Other coroutines are running. Things are happening. The physics system is updating. The whole point is that on a single thread, we want to pause the execution of the current function, come back later, and we want to pause in such a way that everything else can still run. The single thread is not stopped. It's doing other stuff, and it'll come back later. Okay? So, very, very, very powerful thing. So, another challenge for you, and this is the hardest one. Oh my goodness. Okay. And your hint for this one is notice that this big hairy function over here is in a static class. It is a static function in a static class. And look at the names. The names of all these things will help you understand what it's doing, even if you don't understand how the code works under the hood. So I'll give you a few moments. This does something very powerful. And if you have written this coroutine and you're just reusing it, then the code over here is actually really simple for what it accomplishes, okay? I'll give you a hint. This is not a debug example line of code. This is code that the 494 students literally use to do their Legend of Zelda and their Metroid. What does it do? Okay, someone tell me. You don't have to act this one out. You couldn't if you wanted to.
It just moves the object over a set period of time from one position to another.
That's what this function does, yes. This utility function. But what does this do over here?
It moves an object from its initial position to the final position over 2.5 seconds, waits 2 seconds, then moves it back to its original.
Okay, and it does that when you, the player, do what?
When it's a transition, or
Nope.
it's the space bar.
Yes. So this right here does the following. Watch this. I press spacebar, space. The camera, in this case, moves to the next room, and then 2 seconds later, it moves back. Okay? This is that room transition logic that we started the lecture with. Coroutines make this really easy and pretty easy to read. So every single frame of our game, you have a while true loop, okay? This looks like an infinite loop. It would freeze our program if this were not a coroutine. Because every frame, we're going to go around this while loop. But at the end of the frame, we have this yield, return, null at the end of our loop. That means right here, yield, return. So we're yielding. But what does null mean? In Unity, yield, return, null means we wait to the next frame. We're not waiting very long, but we are yielding to the next frame. We let everything else finish running, and on the next frame, we'll pick back up right here where we left off. So we're going around this loop, and every single frame we're checking, has the player pressed spacebar yet? Have they pressed spacebar yet? If they haven't, we just kind of wait and yield. Do nothing. Let everything else run. If you get rid of this line right here, this yield, we do freeze the program, like an infinite while loop tends to do. Eventually, one day, the player presses spacebar. We enter into here. We calculate an initial position, which is where we currently are with our object. We calculate a final position, which is going to be at 20, 0, negative 10. That's like off to the right, okay? We then yield return. We're yielding on a coroutine. And the coroutine we're yielding on is a library function, okay? It's part of the coroutine utilities class, and it's called move object over time. So what object are we moving? The current one. Where do we start? Initial position. Where do we end? Final position. How much time? 2.5 seconds. I'm not going to go through in this class how this works, but it's not that crazy. Once you've done it a few times, it's not too bad. But it moves, it is a coroutine that will move any object you supply from one position to the next over a certain amount of time, and it will do so every frame, okay? So it will execute a while loop that will yield every frame. You get rid of this, you hard lock. The whole program freezes, okay? So we're going to move our camera in this case, because this component is actually on the main camera actor, the game object. So we're going to move, when the player presses space, we move our camera from the initial position to the final position. So we move over like that. We then wait for 2 seconds, and then we move it back, because this is the same call down here as we have up here, just our initial position and our final position have been swapped. That's it. Then we go back to checking for the space bar. If the player presses the space bar while the camera is moving, what happens? Yes?
Nothing.
Nothing. Exactly. Nothing happens, because the coroutine is not even hitting this every frame. No, our coroutine is currently yielding and waiting for the camera to finish moving and then move back. And then execution gets back to this if statement that's checking for the space bar. So you see, if I get rid of this right here, this code is really readable. It's like move to the right, chill for 2 seconds, move back. And it all happens across many frames. It is a temporal mechanic. And we can read it as if it were a grocery list. Okay? Move to the right, and then when you're done moving to the right, chill there for 2 seconds, and when you're done chilling there, move to the left. That's it. Okay, very simple, and you get this really nice behavior. So many mechanics in games are temporal. They occur over many frames, and we really want to be able to program them in this to-do list kind of fashion. In order to do that, we have to have code that can chill and wait and not lose its place. Here's a really, really cool coroutine that I really love writing for some reason. This is a coroutine, and this is a big hint. It's called wait for current enemies defeated. This is a coroutine that you can yield on. If you want to close a door, lock Samus in until she defeats all the enemies in the room. And then you unlock the door after she defeats them. Well, you can lock the door, then yield return. Yield return, wait for enemies defeated. And then after this finishes and returns, you unlock the door. You maybe play some sound effects as well, or spawn in some goodies after the door is unlocked. This coroutine has another infinite loop, but thankfully it doesn't hard lock anything. It doesn't freeze us because of this line right here, yield return null. Let everything else run, and we're gonna chill and we'll try again next frame, okay? That's what that means. Every frame, we're going to use GameObject.findAll GameObjects with tag. This is kind of similar to actor.findAll, which you implemented in homework 7. And we're going to find all the game objects, the actors, that have the enemy tag. We don't have a concept of tags in our engine. We do have a concept of name, which is kind of, that you could treat that like a tag if you really wanted to. And then we're going to look at this array. If the array has a length of 0 or less than 0, by the way, why do I make it less than 0? Anyone know? Some people bug me about this, like, Austin, an array can't have a length of less than 0, right? Right? You sure? I think I have been in a programming language before. It might have been C++, where somehow that length operator or that member can return like negative numbers. I'm not sure if I'm not exactly sure when this happened to me, but I think it happened to me once, and now I'm scarred forever. It works. It's fine. No big deal. Okay, if the enemy array ever fails to find any enemies, we know we're done with this coroutine, and we want to yield. All the enemies have been defeated. They're gone. And so we break out of this while loop, and we're gone. And that's the kind of stuff you can write, okay? You can write conditionals. You can write these really cool checks. If you ever have logic in your game that says, don't attack the player until the dialogue is finished, like you have a boss fight or something, then you could use a coroutine to create that logic. All right? So pretty cool stuff. And there's some other stuff in here as well, blah, 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 blah. Okay, so hopefully, you don't have to understand how to use a coroutine in Unity, because we're not using Unity. We're not using C#. But I hope you at least have a notion of what coroutines are and kind of why game designers love them. Important, why our engines want to have them. It's not a requirement in any homework. I almost put it in. Maybe I should put it into homework 9. Should I do that? That's actually a pretty good idea, I think, because homework 9 is kind of dinky as it is. Lua has default support for coroutines. But there's one really important thing that Lua doesn't do, which is kind of hilarious. If you have experience with Unity coroutines, you're going to slap your forehead. So coroutines in Lua look like this. And it's kind of nice. A coroutine can have a handle, okay? And the coroutine table is built into Lua. So you can actually, even in your game engines now, you could use coroutines. The coroutine table in Lua, it's built in. It comes with a create function, which will create the function right here. In this case, we're giving it an anonymous function. So we're kind of like inlining a function. This is kind of like a lambda function. But you could also hand it a function that you've made. So like self dot, my fun coroutine, right? This is a coroutine that will print hi when it runs. But by default, when you create a coroutine in Lua, CO, we can print that coroutine. It is a thread data type, which is really confusing because I'm pretty sure this is single-threaded, but whatever, okay? Lua and making, strange default decisions and naming decisions, right? Like that's just their thing. Okay, so this gives us the address of the thread object, which isn't really a thread, but it's like a thread state, I think. And this coroutine, importantly, it is not running. It hasn't been started yet. When you create this coroutine, you actually have to launch it. Kind of like in Unity's C#. You can create a coroutine, but you have to call start coroutine in order to actually make it start going and processing. You can print at any time, and this is good for debugging. You can print the status of a particular coroutine object, a thread object, by using the static function coroutine.status. It's a function on the coroutine table. This is not feeling very object-oriented, okay? But that's okay. And you might see that it is suspended. In order to make the coroutine run, you have to create the coroutine, like what's up here, and then you actually have to call resume on it. The coroutine table has a resume function that Lua has given to you, and you have to call it on the object, at which point the coroutine will run until it yields. This coroutine never yields. So you start to wonder, why is this a coroutine if it never yields? What exactly is the point? This is just a fancier way to call a function, right? It's just in the call stack. If a coroutine doesn't have a yield, it probably doesn't need to be a coroutine at all. It can just be a normal function that you call. So we call .resume on it, and then we get hi printed in our console. We can then check the status of our coroutine, and we'll see that it is dead. The coroutine is dead because it ended. It hit the end, right? It cannot be revived. It's done. So here's a more interesting coroutine. Coroutine right here, coroutine.create, we provide this kind of inline anonymous function. It's going to go through, it's going to iterate through in a for loop from I equals 1 to 10. It's going to print that number right here. It's going to print co followed by a number, and then it's going to call coroutine.yield. This is a function in the coroutine table that will take whatever coroutine is running when it gets called, and it will suspend that function. It will suspend that coroutine right then and there, okay? So when we create this coroutine and then we start the coroutine using resume, we're going to get printed co1, okay? But then it stops, and the coroutine suspends right here, and it will not move on. In order to get the next number, co2, we actually have to call coroutine.resume on that coroutine to get it going again. And this is the biggest difference between Unity's coroutines and Lua built-in default coroutines. In Unity, if we suspend, if we have a coroutine that yields, Unity will automatically resume it on the next frame, or however much time has passed, okay, for that coroutine. Lua will not do that automatically. We have to do that automatically, or we have to set it up and make that call ourselves. So it will not keep going. We will not see the rest of the co numbers, 1 through 10, until we call coroutine.resume. Now, what you could do is you can create a coroutine manager. And at the start of every frame, we will look to see what coroutines are out there that have suspended, and we will resume them automatically. That would give us Unity-style coroutines. And I'm going to show you how we do that in just a sec. But that is, I think, the important stuff. You can pass parameters into coroutines just like you normally do, or just like we saw in C#. And you can read other stuff about coroutines there. But what I want to do, because we got 9 minutes left, is I want to show you, okay, really quickly, that coroutines are a thing in C++. Whenever I look at these, like the syntax looks weird to me. It looks weird. Co-yield, while true, n++. Yeah, everything just seems a little bit strange to me. I don't use C++ coroutines. I need to study C++ coroutines because for the MMO architecture class, coroutines are critical. Why? Just like JavaScript, we're going to do a lot of waiting for stuff over the network, okay? In fact, we might have some dialogue options that the server sends to the client. And we're waiting for the player to decide what they want to say to this NPC character. And we somehow need our server code, C++, to let Lua code wait for that response, for the player to make a choice. So we probably need to have coroutines in our C++ code to power coroutines in the Lua side of things. I'm not entirely sure we need that, but I think we might need that. So anyway, you can do this kind of thing in C++. That's the only thing I want you to know, okay? So I want to download a project, okay? I want to download a project that uses coroutines. This is a game that uses coroutines. Hopefully it runs. And look at this. It's just another darn resources folder. So I can just go find any version of my engine, like Doodle Jump 3. I'm going to actually create a copy of this. Okay, here we have, let's go coroutine example. I'm going to come in here and I'm going to delete the resources folder there, and I'm just going to drag in a resources folder here. And I'm going to unzip it just like that. Okay. Yeah, that's fine. And I need to rename this because the game engine will not find resources 4. I wish we could put multiple resource folders in here with slightly different names. And then if the game engine discovers there are multiple, it opens up like a game selector. Like, hey, you've activated the A2 engine. Which game do you want to play? Because I found multiple. Oh, that'd be awesome. But beyond the scope of this class, because any feature I add to the engine is a feature you have to make. So I can't just willy-nilly start adding really cool things to the engine without thinking about, oh, which assignment are we going to do those in, and which test cases are we going to have to auto-grade that, and stuff like that. I realized when I was making that security guard game, test case 7C3, that I was actually relying upon some undefined behavior. It related to what happens if you call getComponent on an actor that has been destroyed or deactivated, set inactive. And in my engine, that returns a null, which is useful for kind of checking if the actor is inactive, because wouldn't you know it, we don't have a way of checking from Lua whether an actor is active or not. You'd think that would be something I would have added. I should have added that, but I forgot to. So how do I know if an actor is like dead? It's in my list. I have a table of actors. An actor, for some reason, becomes inactive. It gets destroyed. How do I know to remove that from the table? The actor is still in there. It's dead, but I have no way of checking whether it's dead. So what happened is I discovered I could call getComponent, and if I got a null, if I got a nil value, that meant in my engine that the actor was actually dead. Or it meant that the component didn't exist on the actor, but for my cases, it was fine either way. But what I discovered was that I can't do it that way because your engine might not return nil. It might do something else. That is undefined behavior. The assignment spec, the engine specification does not specify what you're supposed to do if the actor is inactive and you call getComponent on it. That's just not something we specify or test. So we can't build any sort of test case that relies upon that behavior, because then I will put that test case in front of your engine, and if you made a different choice, which you could totally do, totally innocently made a different choice, you explode, and it's not your fault. Anyway, I hope this is giving you a little bit of an appreciation for what undefined behavior is. Have you ever heard of, like, you're using undefined behavior? Most compilers are going to handle this just fine, but they're not required to. And not every compiler is going to do it exactly the way that the other ones do, right? That's why undefined behavior is so scary. And if you accidentally build a program that relies upon that undefined behavior, you're in big trouble. Because in the future, you might use a different compiler, and your program is going to work differently because you used a different compiler. That's really scary. Anyway, let me run this real quick. Okay. And it just immediately stops. Well, that's not so great, is it? But what's going to happen here, or what should happen here, let's go ahead and look in our scene. If we look in our scene here, I'll zoom in so you can see it a bit better. We have a coroutine manager component. And wait, does this exist? Do we actually have this component? What's that?
It's just, there's 2 resource folders nested inside of it.
What? Oh, that explains it, doesn't it? Yeah, it's not meant to handle that. So let's what do I do? I'm going to grab all this stuff and I'm going to bring it out into the top resources folder. There you go. That's the play. I'm like, if I drag it onto the desktop, I'm in big trouble because of this right here. If I drag it out here, I'm in big trouble because this folder is right here with the same name. So let's run this now. Okay, here we go. So it says downloading. AI loop is running. Downloading loop is running. AI loop is running. Is it going to say download complete? That would have been cool. I should have done that. But you can see here that in the early going, we have multiple functions running at the same time. And now one of those has ended. The download has finished, and now we're just running the AI loop, and we're running it every second or so. I want to look at this code. So let's go in and look at the component type coroutine manager. And the coroutine manager has a bunch of stuff going on. But in this scene, we have the tester actor, and it has the type tester on it, the component tester. So let's look in tester. Hopefully it's a simple function. I think it's going to be. So look at this. We have on start, and we launch a coroutine. We create a coroutine called self.doAI. And we create another coroutine called self.doDownload. These are just 2 functions. So we're running these 2 functions at the same time. And this function, doAI, it's going to run forever while true. Wait for 2 seconds. Okay. And then print AI loop. We have another function we're running at the same time called doDownload. And this is only going to happen 3 times. It's only going to go around the loop 3 times. Here's our while loop. We're going to decrement that variable. It is a local variable, so don't panic, okay? Marked local right here. We're going to wait for 1 second. So this is not waiting quite as long as the other one, which waits for 2 seconds. And we're going to print downloading. So if this is basically kind of creating what feels like a multi-processing situation, where we have multiple functions seemingly running at the same time. But actually, it is single-threaded. Okay? Awesome. That is super, super cool. We could have one coroutine yield on and wait for another coroutine. We don't do that in this example, but we could. And so let me run it one more time and just watch what happens. We're seeing both of these outputs. They're interleaved. AI loop, downloading, AI loop, okay? Downloading finishes, and the AI loop is coming every 2 seconds. It feels like they're running at the same time. Awesome. Absolutely sick, okay? It makes the engine feel really powerful. Now, how is this working? Well, we're calling create, and that's it. We're calling create on these coroutines, and then we don't have to worry. They just come back to life. We don't have to call coroutine.resume on them to wake them back up. No, in this scene, there is our coroutine manager that you can download either from this project or right here, okay? Because here it is, right here. And what's happening here, do you know why I made it 00000 underscore? Yeah.
Just to make sure it's like the first thing.
Yeah, yeah. This coroutine manager really wants to be the first thing that you run in the frame, okay? It really wants to be the first thing to run in the frame. And that's because it really wants to look at what coroutines are out there and then run them, and then everything else in the frame can run. And that's just how we kind of set this up. So let's look inside of that coroutine manager and see if we can figure out what's actually happening inside of there. Okay. Oops. Let's go. Here we go. Resources. Component types. Coroutine manager. This is a big, scary component. You don't need to understand everything that's happening here. Okay. When we run the game, we check to see if there is a component, a coroutine manager already in existence. And if it already exists, we destroy our current actor. What is this? This is the singleton pattern, which we show you in EECS 494. Basically, how do we make sure that there's only ever one coroutine manager in existence? If there are multiple coroutine managers, things are going to get funky fast. So we need to prevent that, and here's how we do it. We have a bunch of comments explaining this too. If this variable is nil, then we come in here. We are the first coroutine. So we set this variable to be our actor. This guarantees that we'll be the only one to ever exist. We mark our current actor, don't destroy it. If we ever go to another scene, don't destroy this actor, okay? We don't want to have to make a new coroutine. That would stink. Now, we create a global table called underscore underscore coroutines. Do you know why we put underscore underscore here? It's kind of a weird way to start and prefix a variable name, right? Why?
Some sort of meta table stuff?
No. This is just a way to prevent this system from exploding if someone accidentally creates a global variable that they happen to call coroutine. Who knows? Someone might do it. By putting underscore underscore here, no gameplay programmer, no game designer is ever going to call a variable this, probably. So this probably keeps them safe from accidentally blowing themselves up. Okay. We then create a global variable called coroutine manager. And actually, this makes me nervous because we're already creating this here. But we're creating another table, and we have a function inside of it called create. This is the thing we call to establish and start running our coroutines. So how does it work? Well, we give it a function. Inside of this coroutine.create function that we created and designed, we use the built-in Lua functions. Okay? In other words, we're taking what Lua gives us by default, we're creating a nice abstraction layer on top of it that gives us some additional features. So we create that coroutine using the function that the game designer gave to us. We insert that new coroutine into a table. Which table? The underscore underscore coroutines table that we created earlier. Okay, that is a global table. We then resume that thing immediately. That is starting the coroutine. Okay? We do this because we don't want our game designer to have to remember to launch it. Chances are, if they're creating the coroutine, they want to run it right away. Okay? So we launch the coroutine. We can get some error messages and some checks out of this, by the way. Sometimes the coroutine can't run. All right? We pass those parameters that were given to us into that coroutine using table.unpack. Okay. We check if it's not a success, we remove that coroutine. We don't want a nasty, awful, broken coroutine in there. We might have reasonable ones in there. We don't want a bad one in there. And we print the error message so that our game designer knows something went wrong. We then return a reference to the coroutine just in case our game designer wants to stop it later or halt it or do something else with it. Or print the status of it. So in our update function, notice this is not on update. This is an update function. Coroutine manager.update. We're going to look at any coroutines that might be dead. We're going to keep track of any coroutines. This is the this is the collect then alter pattern, but in Lua. We're going to look through all of the coroutines that we have in our table, all the coroutines that we know about. We're going to check to make sure that their status is still good. If their status is suspended, then we need to resume them. Okay? We are going to automatically resume those coroutines every single frame. If we can't resume them, we're going to put them into the dead coroutines table. If the coroutine is marked dead, as in it's finished, it's got nothing more it wants to do, then we put it into the dead coroutines table. At the very end of all of this, we go through our dead coroutines table and we remove them from our list. And it looks like to me like we're going backward through this list, like we saw in the collect then alter lecture, okay? All right, and then we have some convenience functions. We can wait for seconds. This is the function we saw some of our coroutines using to just chill and wait. We can provide this is a global function, first of all. It doesn't have a self-reference, and it takes the number of seconds. We use os.time to check whether we have progressed the number of seconds we want to. We yield, and when we're done with this, the coroutine will stop. So there you go. Finally, we have the onUpdate function, which again, just like any normal component, our game engine is going to call for us. And the only thing we do in here is we call into this update function within our coroutine manager table, i.e. this update function is right here, okay? We want to do this. We hope that onUpdate is called first thing at the beginning of every frame, which is why we named it what we did, okay? I think doesn't the name determine the order or something? Does it not? I've ever forgotten that.
Of the
actors?
name?
No, actually, you know what? I think this is wrong. The name doesn't determine when the actors move and update. We really hope that you're going to put this at the top here. But I think it would probably be okay if it wasn't at the top. There might be some like off by one frame things. But and there are probably some ways I could have solved that as well. But that's how it works, okay? Okay, you don't need to know this for the exam. What you do need to know is that by default, Lua coroutines must be resumed by something. And if you don't have a coroutine manager in here in your game to do it for you, then you're going to have to do it yourself. Okay? There's a difference between a coroutine built in and a coroutine manager, which makes sure they're all running properly and getting woken up at the beginning of each frame. Okay? That's probably the thing you want to remember for the exam. All right? And maybe the quiz. We'll see. Anyone have any questions about this stuff? You probably have questions, but I think you know enough now. All right? Coroutines are awesome. It makes certain mechanics that would have been very difficult and ugly to implement and very bug prone, makes them easy peasy to implement. And if you take 494, you're going to get a lot of experience with coroutines. Okay? Vadim, do you use coroutines in your P3?
I think I do, yeah.
Yeah. They're quite nice when you get used to them. Because a lot of things in games want to happen over many frames or over time, and not just all on the same frame as fast as it can happen. Okay? So it makes writing your logic really elegant. Okay. Everyone, that's all she wrote. When we come back next week, we're going to do that quiz, but we're also going to start looking through our exams. The lectures next week are not going to be very long. They're not going to be very deep. We are going to be going through the exams from previous semesters, and I'm going to be talking through those problems, what you should be thinking about when you're doing those problems. And so what I recommend is see if you can take a crack at those problems before you come to the lectures next week, okay? Take a look at them, take a crack at them. They'll be more meaningful if you attempt them, and then I fix your mental model of what's happening, versus I spoil them for you, and then you kind of don't really attempt it yourself. I know it takes a while to attempt an exam. They're kind of long exams. But if you want to know where those exams are, they're listed publicly on the internet. I don't know if I'm going to regret that someday, but there's this exams tab on the EECS404.com website, and you can actually find the exam, and the exams are broken up into a question packet and an answers packet, and then the answers key as well. So you can grab the question packet, and you can grab to get the questions, you can grab the answer packet. This is where you write the answers and actually click on things and circle things with your pen and paper. And then you can get the answer key, which actually has the answers circled for you and the code written in here for you. I split these things up because the students told me it was a pain in the butt to keep having to go back to read the question and then going forward, flipping through the exam to write the answer. So now where you write and select the answers is separate from where the big questions are described. Okay? Question?
Yeah. Are those exams indicative of what the exam will be this time around?
Definitely. Yep. Pretty much. I'm running out of material, new material. So eventually, it's literally the exam is going to become a remix of a previous problem. That might not happen. That might not happen completely on this upcoming exam. But like, I'll tell you, the stuff on the new exam that I've already written is like, I took an old problem and I spiced it up a little bit. I changed the topic slightly. That's it though. So, all right. I think eventually all exams become that way. Because here's the thing. I could have kept the exams hidden from the internet. But what that actually does is it just crazily advantages the students who can get access to the previous exams. Which, students get a copy of their exam, right? They take them home. If you've got a friend who already took the course, you've got access to previous exams. And all the other students don't have access. And that sucks. I think that's not fair at all. So the way to do this fairly is to give everyone access to the exam and then do my best to come up with new, interesting questions. But eventually I run out of material. There's only so much content and topics in the course. So how do you create an infinite number of questions from a finite number of ideas and topics? You don't. So anyway, I will see you all next week. I will see you on Sunday if you want to hang out on Sunday at the office hours. Have a great weekend. If you're a bit behind, don't give up, okay? You've got all of next week to try and knock those homeworks down. And homework 9 is a fast one, okay? If you can reach homework 9, you've got a shot. So good luck. Have fun. Homework 8 is pretty easy too, it turns out. Not easy, but easier. See ya. Okay, everyone online, thank you for watching. If you are not a University of Michigan student, you don't have to worry about the exam. So hey, lucky for you, right? Or maybe unlucky, because that pressure the exam puts on you is a big part of like getting you in there and really getting to understand and grind these topics again. So if you don't have that, maybe you're actually the unfortunate one. So in any case, you can always take the practice exams online, and I'll eventually post the exam for this semester there as well. Anyway, take care. Bye-bye.